Hello class, today we'll be covering on the last part of turning effect of forces, which focuses on 5.3 center of gravity for our home-based learning. But before we start our lesson, let's do a recap on what is a moment. As per the only formula in this entire chapter, the turning effect of forces known as the moment is calculated using the product of the force and the perpendicular distance from the pivot to the line of action of the force. Now, most students have difficulty with finding the perpendicular distance. So, right now, can you use the two-step process to find the perpendicular distance for these three examples? Alright, so pause the video right now and then try it out for yourself. Okay, so if you've done so, now let's do the two-step process for each of these. Okay, so for example A, we have our 10 newtons here and the arrow to signify the force. So first we take a ruler and we draw the line of action cutting through the arrow. Okay, next thing we identify the pivot and then we draw a straight line from the pivot all the way to the line of action, which is here. And then we realize that this is just the perpendicular distance, which gives us a distance of 5 meters. Okay, now let's look at B. Same thing, our 10 newtons force is here. We draw a straight line cutting through the arrow. And then we find a pivot and we draw a straight line to this red color line. And notice now, we have our perpendicular distance, alright, which is then 3 meters. Now, we go to our last example, example C. Same thing, we draw a straight line cutting through the 10 newtons force. And we realize for this specific example, at the pivot, the force actually cuts through the pivot. Is there any perpendicular distance for this case? Okay, so this is actually a special case. Wherever the line of action cuts through the pivot, the distance is actually 0 meters, or in fact there's 0 distance. Hence, there will not be any moment. Alright, now let's go on to a next important concept for this entire chapter. Alright, which is the principle of moments. Okay, this is extremely useful for all moments related question, as it states that for any object in equilibrium not moving, the sum of clockwise moments about a pivot is equal to the sum of anti-clockwise moment about the same pivot. Now, why is this so useful? Because it helps you to create an equation, and this equation helps you to solve for missing unknown forces or distances. Alright, so let's take a look at an example here. Okay, we apply principle of moments to this question. Okay, since this is a recap, you can stop the video to try to solve for the missing force. Right, give some time to try it. Okay, so now let's try to attempt this together. First, we identify the direction of the moment created by each of the individual forces. So let's take a look at F. We first identify the force, the direction of the force, as well as the pivot. And then we move in the direction of the force around the pivot. Do you notice this is actually going in a anti-clockwise direction? Hence, we can identify that the force F produces an anti-clockwise moment. Next, let's look at the force 6 newtons. Find the force, locate the pivot, and move around the pivot in the direction of the force. In this case, what motion is this? You may be quick to realize that this is actually a clockwise moment. And last, you can repeat the same step with the 4 Newton force, and then you also get a clockwise moment. Now, next, let's apply principle of moment, since this entire system is in equilibrium. So by principle of moment, the sum of the clockwise moments equals to the sum of anti-clockwise moment. With this, we can now form our linear equation where we find the moments for each of them. So we take the force multiplied by the perpendicular distance to get 6 newtons times 0.6 meters. Next, we get our 4 newtons multiplied by the perpendicular distance. In total, we add 0.6 meters and 0.4 meters to get 1 meter. And lastly, we equate onto the anti-clockwise moment, which gives us force multiplied by 0.8 meters. Using algebra, we can actually solve to get a F value of 9.5 newtons. Okay, now let's move on to the lesson objective for today, okay, which is on center of gravity. So over here we have a very innocent looking wooden ball. Okay, what's so special about this wooden ball? Nothing much. But if we were to zoom into the wooden ball, we get to see atoms arranged in a very orderly manner befitting of a solid. Okay, if we were to draw the gravitational force acting on the ball, it can be represented by the force acting on each individual atom, where the weight or gravitational force is acting downwards. However, this diagram is not very useful for calculations in general. As such, physicists have used the term center of gravity, which is defined as the point through which an object has its whole weight acting on. What does this mean? Alright, this simply means that we take all of the weight acting of all of the atoms in this entire object and we average it out. Alright, so the center of gravity, or the position of the center of gravity, is the average position of all the atoms in this object, which just so happens to be the center for all uniform objects. Alright, so in this case of this wooden ball, we have the center of gravity right smack in the center, and that is where the weight acts on it. Right, just so happens to be the average position of all the atoms. Alright, and here are some examples for center of gravity for some uniform 2D objects as well as 3D objects. Okay, interesting to take note of is that for objects, alright, with a hollow center, it is possible for the center of gravity to be acting in empty space. In the case of the ring, the center of all of the atoms in this ring just so happens to be in the center where there's no material. So it is not abnormal to find the center of gravity acting in a space where there is no material at all. Okay, now let's move on to an example. Alright, let's say I have a ruler. Okay, this is a very uniform ruler, uniformly distributed, and I want to balance it on only one finger. How do I do so? Okay, first, let's break down what does it mean to be uniformly distributed. It just means that the center of gravity acts directly on the middle of the object, since the atoms are divided equally throughout the ruler. Okay, next, let's position our finger near one of the end of the ruler. Okay, now would the ruler be able to be balanced in such a position? Okay, you'll probably know the answer, but try to explain the reason using moments. Okay, pause the video if you need some time to think about how to use moments to explain the motion of this object. Okay, and the answer is that the ruler will not be balanced. And why is this the case? It's because the weight which acts upon the center of gravity actually creates a clockwise moment about the pivot, which is where our finger is. And this net clockwise moment then cause the object to be unstable and will rotate in a clockwise direction. Now, what if I shift the finger into a new position where it is directly underneath the center of gravity? Once again, okay, the answer is already here. But yes, in this new position, the ruler would not undergo any rotation, because now the weight is acting directly in line with the pivot. As you may know, from our previous example, when the weight is in line, alright, the line of action of the weight is in line with the pivot, would there be any perpendicular distance? Okay, the answer is no. and since there's no perpendicular distance, there'll be no moment created about the pivot, resulting in no net rotation. Alright? Okay, using these two examples, now let us tackle the fork and toothpick trick. Okay, so this is a recreation of the experiment in my house. And here are some guiding questions to help you debunk the magic by yourself. First, let us ask, where is the pivot in this system? And where is the center of gravity for the fork and toothpick setup? Okay, I give you some time to think about it. Now, gather some thoughts. You can pause the video if you like more time to think. Now, most of you may be able to identify that the pivot is the contact point between the toothpick as well as the pen, because this is where the object will rotate about, and if it were to fall off, it will fall off at this particular point. However, the center of gravity is the tricky one. Right? The hint is, the concept is similar to what we just covered just now with the ruler and the finger. Okay? Without further ado, the center of gravity is right underneath the pivot. Alright, if we draw a vertical line cutting down the pivot, the center of gravity should be somewhere along this line. Now, why is this the case? It is because the only way for the entire system to be in equilibrium, if the weight acting at the center of gravity does not result in any net moment. And for the only way for it to happen if the perpendicular distance from the line of action of the weight is 0 with respect to the pivot, where the line of action cuts through the pivot. In such a scenario, there is no net moment, hence the system is in equilibrium. Now, why is the center of gravity shifted so far backwards and so far downwards in this fork and toothpick example? The trick lies in the fork being slanted sideways and downwards. So when it's slanted downwards, it's actually shifting the center of gravity slowly to the bottom. And the reason for the forks being spread left and right is such that the center of gravity lies somewhere in the middle of this setup, hence shifting the center of gravity right below the pivot, allowing it to be balanced. Alright, so this is the end of our home-based learning. Alright, remember to go and try out the Chapter 5 Worksheet 1, alright, and then submit to me on Thursday.